1. Okay? And the solar radius, although it's extremely difficult to define the solar radius, but the typically quoted number. Right? Is that correct? Can you work out the density of the sun now? The average density of the sun? Can you do it? Can we do it together? Very quickly. Yeah? This is 3 multiply. Right? Okay? This is 350. Is that correct? Right? So how much do I have here? I have 9. This is a 9. This is 10 to the 32. How much is this? This is 1. What's this density? Water. This is water. The average density of the sun is water. That doesn't make any sense because the sun has actually a density profile, is not a constant, but a good approximation is that the average density of the sun is water. Now, take this mass, which is more or less the mass of a supernova progenitor, and it may vary by a factor 10, so still you're going to get the right answer in astrophysical terms, and slam it into a neutron star. What's the radius of a neutron star? 10 kilometers. So in centimeters, is that how much? Say the number. So 10 kilometers, 10 to the 3 meters, 10 to the 2 centimeters, right? How much does that do? 6. You can sum numbers, that's amazing. Yeah, it's 10 to the sigma. Okay? 10 to the 6 centimeters, okay? Now, do this now. I'm not going to do it. Slam this mass into this volume. Okay? And get the density. Pasquale already got the answer, gave you the answer, Esther. While you do the number, I give you a way to compute it. It's 5 orders of magnitude difference, so it's 15 times bigger. So basically, I can tell you that the density of a neutron star is going to be 10 to the 15 grams per cubic centimeter, approximately. Okay? Which is a lot bigger, and I frankly cannot figure out by mind experience what it is. Now, these numbers are important because if you compare, what's the interstellar medium density? We said 1 particle per cubic centimeter. So the density of the interstellar medium is 1 particle per cubic centimeter. How much does a particle weigh? Let's say it's a proton. 1 GeV. How many grams is a GeV? We said it earlier. Okay? So, this is if you do the mean-free path, right, which is 1 over the particle density, not the density, not the weight density, and sigma, okay? Right? Say it's protons, it's all protons, so you can easily convert each of these densities into a particle density, right? And then you take the characteristic cross-section of whatever force acts in that environment, you can compute the mean-free path. If you do it for this, you find that this is opaque even if you adopt weak interactions. Okay? You find that this mean-free path is going to be smaller than the characteristic size. So whatever is interacting even only weakly is not going to get out. Whereas if you take this number and you adopt even an electric force, you find out that this is actually non-opaque, so it's collisionless. This is the sort of exercises that you have to do, and this is very easy to do. Now I'm going to leave the stage to Pasquale 2 or P-bar before they eat me alive.
Can you hear me? A little bit higher? Better? Okay. So today I would devote most of the lecture, if not all, to say again what I said yesterday, but in a different notation and with some more details. So to derive a propagation equation for the cosmic rays, accounting for this major fact, which I hope I managed to convince you about yesterday, namely that there is a diffusion due to this perturbation, right? Which Pasquale mentioned today are in fact more physically the Alfvén waves that propagate in a magnetized medium. And the key result that I obtained yesterday, just as a little reminder, I would put it here, is that there is a diffusion in the pitch angle scattering, or equivalently a diffusion in terms of the angle of your cosmic ray with a rate nu, which can be estimated to be omega, the relativistic cyclotron frequency, times the delta B over B0 square, evaluated at this resonant wave number corresponding to the little picture that Pasquale redrew a few minutes ago. Okay? So the cosmic ray movement is a diffusion. The angular coordinate of the cosmic ray varies with a rate given by this function, or equivalently the pitch angle. I remind you that this is nothing but Pz over P, and this is nothing but the cosinus of the angle that the cosmic ray forms with respect to the regular magnetic field, varies with that diffusion coefficient. Okay, this was the bottom line of what we discussed yesterday, and we also said that this is a collisionless diffusion. So again, today, this morning, this term came back into the game. Now, using the notion of Vlasov equation that was introduced this morning, I would rewrite this in terms of the transport equation for the particle distribution function. Okay? So basically, we got convinced that the Vlasov equation is nothing but a way to rewrite the conservation of particle number in phase space. Okay? So in terms of this f of x and p, if you multiply this by the volume element in phase space, this is a dn, and this is conserved, okay, in the evolution. That's the summary of what the discussion this morning was in its first part. And then, if you remember what we did yesterday, was to do an evaluation of the evolution of the cosmic ray using a sort of perturbative approach around the unperturbed solution of the motion with respect to this constant magnetic field. And during the derivation, I also introduced this ensemble average. So I mentioned the fact that you may have a random wave with a random phase. We take some average over that. And also, during the derivation of this result, I use the fact that I am only interested over time scales which are much longer than the typical gyro period. Okay? Now, this means that, in fact, the result that Pasquale wrote for F is not directly applied to what I discussed yesterday, but rather that my F, I should more correctly write as this ensemble average distribution plus an additional term, delta F, that describes the deviation with respect to that. Apart from this, I can apply the Vlasov equation. So I plug this decomposition into the Vlasov equation, okay? And I will get, in general, an evolution for both F and delta F. From the discussion of yesterday, we will only be interested, in fact, to the evolution of this quantity. And so this is what I'm going to focus on. If I do that, by definition, of course, the delta F is such that if I do the ensemble average, and this is to be meant in the same approximation I did yesterday, this is going to be 0, okay, by construction. Good. So I plug in this decomposition in the Vlasov equation, and what I get is derivative with respect to t of this ensemble average plus v dot gradient of this f plus the force term, okay? And I write it directly in this form. Bear with me for a second, and I'll justify it. Dot gradient of b average f equal the ensemble So I just do basically apply this ensemble average over the Vlasov equation, written in terms this time of F is the cosmic ray distribution. Okay, so I'm starting to implement the second step of what Pasquale was mentioning. What is this omega vector here? This is Q B0 over the energy, and delta omega is Q delta B over the energy. This is just the Lorentz force. Here is a force term, and this is just the Lorentz force. If you do not recognize it, you might also remember the cyclic identity for the vectorial product. So this you can rewrite, C dot A cross B, etc. All the permutation, the cyclic permutation, etc. And this term I cannot neglect a priori if I want to have a non-trivial evolution for my my ensemble average piece of the Vlasov equation. Okay? So this might look formal to you, but I hope that after the discussion of this morning, it's a little bit more clear what I'm doing. This is just the evolution of the ensemble average part of the distribution function subject to a constant magnetic field, which is my force, plus this residual term that I put at the right-hand side, which is the impact of this perturbation on my distribution. Okay? Just a comment on the meaning of this term. This might look a bit obscure to you, but actually this is nothing but describing the precession around the magnetic field. So one way to realize this is that this can be also written as e to the minus 1 qb times p orthogonal gradient p orthogonal. This is a simple exercise you can show. Okay, this one is equivalent to this one, so it only affects the movement orthogonal to the direction of the background field. And also there is another way to write it, which might be more familiar from some quantum mechanics study. So if you define the angular momentum operator, minus I p cross gradient p, you can also rewrite this term as, okay, this term here can be rewritten as minus I omega L acting on average F. And this term here can be also rewritten as I delta omega. This is not important, it's just for you. Maybe sometimes you see these terms written in this way in the literature. So these are just equivalent way to rewrite this term, which stress the importance of the fact that this is basically a sort of gyro motion around the direction of your background field, and this is the analogous term in terms of the perturbations, okay? So far, so good. So the whole discussion of yesterday has a purpose today, for me, to justify a couple of ways you can write this term. Because you see, the key point here is that we want to rewrite this term in such a way that it only implies our ensemble average F, because otherwise we would have a coupled equation for delta F, and we don't know what to make of it. So there are a couple of ways you can proceed, which require using the heuristic derivation of yesterday. What do we learn about the effect of fluctuations yesterday? We learned the fact that there is a diffusion in pitch angle, or equivalently, that there is a rate of change of your angle with this frequency. Okay, this is an inverse of a time, dimensionally. So this justifies heuristically the fact that I can rewrite this term in two different ways, at least. One way, can I erase this exercise? Okay. What does this term do physically? This term, I argued, is a diffusion term in the pitch angle. So in principle, I can write it in terms of a diffusion term in the pitch angle. So I will just write it down and then justify it. So this can be written as a diffusion term in the pitch angle in the one-dimensional approximation of yesterday. Or alternatively, you can have even a more intuitive physical picture of what's going on by saying that this is basically a term that tends to isotropize my distribution. Why? Because with this rate, you change your your angle. So naively speaking, I would tend to believe that my cosmic ray, starting rather anisotropic, will be driven toward isotropy with a rate characterized by that nu. Okay? So another way to write this term, these are different approximations of this term, which basically are equivalent. I will show you in a few moments. Let me write it this way, where n I have introduced as the integral, the angular integral of my ensemble average f. So what does this term do? It tells you that my ensemble average f will tend to its isotropic mean with a typical rate given by nu. This, on the other hand, is a typical term that you find in diffusion equation, okay? Have you seen the heat equation, for instance? This is equivalent to say that this d mu is the diffusion coefficient in pitch angle variable, okay? So they look quite different, right? But in fact, they describe the same type of physics. So what I'm going to show you is that as a result of either this approximation, we end up with a diffusion equation for this variable here. And we will learn what is the spatial diffusion coefficient in these two approximations. So let me start from this second one, okay? So let's assume that this is valid, and let's also introduce a variable for this difference, if you wish. So I will introduce another angular average, which I will call J, so that the average f will be decomposed as 1 over 4 pi n plus 3 p over p j. And j here is a current, obviously. And this is nothing but the angular average of P versus F, ensemble average. Okay? So this is just a name I'm giving. If I plug that decomposition into this equation, I end up with equations for both the variable n and j, and I collect these two equations in order to separate the two. I can write these two in terms of derivative with respect to t of the density, the angular average density, plus gradient, this is spatial gradient, of j equals 0. You would recognize this form in the same thing that Pasquale just wrote before. This is a conservation equation, okay, for the mass. And then the other piece would be the time derivative of j plus 1/3 of the gradient of the density plus a term which is omega cross j, approximately equal to mu theta theta j. This is approximately equal because I'm doing this ansatz, which is not exact, okay? This comes from replacing this approximation here, plus this ansatz for the right-hand side, into this Vlasov equation. Again, don't be scared if you miss one line, because there will be notes with step-by-step derivation of these things. Now, there is another observation which has to do with orders of magnitude. So the macroscopic time variation of your currents is very long with respect to this term, which is very fast, in fact. if you remember this estimate here, this guy has a typical number which is of the order of the hertz. Huh? So basically, there is no way a plasma, macroscopic plasma in astrophysics is going to vary on much faster time scales. So basically what I'm doing here in order to close this, this system is to neglect this term with respect to this term. And if you do that, you end up with the following conclusion, that the I component of your current will be equal to minus chi I L of the derivative with respect to L, space derivative, of n. I don't know if you recognize this, but this is what you might have found in basic physics as Fick's law for the diffusion. This in vectorial form would be something like that. If this is a scalar, this would be just that. Okay, you might have found this in macroscopic description of diffusion of you know, the example we made yesterday. You open a bottle, you start smelling something after some time. And the other equation, let me erase this, which is not general. Let me introduce in a second what K is here. And the other equation comes from plugging this into this. And you get the derivative with respect of time of n is equal, derivative with respect to I, chi e j, n, derivative of j. No, sorry, derivative of j, here. If this does not depend on space, this is the standard heat equation. You might have seen this in many, many instances. What is this K? Well, this comes from the inversion of this, okay? And the tensorial form of this Kj, I write it down. It's the inversion of a matrix, nothing particularly deep. This is the Levi-Civita tensor introduced before. Okay? This tensor has some eigenvalues. And these eigenvalues are 1 over 3 mu theta theta and 1 over 3 mu theta theta plus or minus I omega. Okay? This is the one that describes the diffusion parallel to the background field. Okay? So let's try to stop for a second and interpret what we got. As a result of this decomposition and these heuristic ansatz for the description of this effect of the fluctuation, which was justified by the discussion of yesterday, we arrived at the conclusion that the density, if you wish, in phase space, ensemble averaged and angle averaged of the cosmic rays is described by a sort of heat equation, this one, more generally, where there is a diffusion coefficient. This is now a spatial diffusion coefficient. These derivatives are with respect to xi, xj, etc. This is a spatial diffusion coefficient here. And this spatial diffusion coefficient is roughly 1 over the angular diffusion coefficient. Now, does this make sense or not? If I tell you that a particle is changing its direction very frequently, what do you expect? That it moves very far away or not? If it changes the direction very frequently, it stays almost stuck at the origin, right? If the particle changes its direction quite slowly, then it means that the particle propagates quite a bit in space. So the spatial diffusion coefficient, it makes sense that it's inversely proportional to the angular rate of change of your direction. So this is not a crazy result, the one we got. And then this is a more formal justification of what I told you yesterday, that actually in space, the cosmic ray distribution, appropriately, ensemble averaged and angular averaged, evolves like a heat wave, if you wish. So nothing so crazy. You have an overdensity of cosmic ray there. You wait some time. It evolves in time, smooths out with some typical coefficient, which depends on how fast your cosmic ray direction can change. So these all make sense, I hope. Okay? If you are lost in the steps, just retain this final result, which here I never made any other physics assumption, but this one, which was basically justified based on yesterday's discussion, and this one, which is, again, justified based on yesterday's heuristic discussion. So far, so good. So let me erase this second step, which is not really relevant for what I'm going to say. And let's justify briefly the fact that if we used these other ansatz for the right-hand side, we get basically to the same result, okay? With a different expression. It's a more macroscopic way of dealing with it for the Kj, this time not in terms of mu, but in terms of this d mu mu. And directly in terms of a 1D problem, because that's what I did yesterday in order to get to this d mu mu. Okay, so let's do the same exercise. Now, instead of plugging the second expression, I plug the first expression here. Okay, and I can also write directly the problem in terms of 1D, because that's what I did. So the only space variable that matters for this appropriately averaged distribution is the z variable, okay? And the other variable which is pertinent is, of course, the mu variable, the angular one, okay? So let's rewrite this just in terms of this more simplified distribution. And so what we get is just the derivative with respect to t of f plus what? V mu derivative of f with respect to z. Remember that v times mu is vz. Huh? Equal, why now this term is 0? Because I told you that this term is describing just the gyro motion around the axis. So it's irrelevant to describe the z evolution. Huh? So I just write down the component I care about. Huh? This is equal to d mu mu df over d mu. And then I do something similar to what Pasquale did previously. I take some moments, or averages, if you wish, of the angular dependence of this. Why I do that? Because, again, I've argued before that in order to get to my diffusion equation, I'm considering, in fact, the angular average of my ensemble average distribution. So I repeat the same thing in this case. So I can define f0, which is now dependent on t and z, but not on mu, as the integral, or maybe 1/2 of the integral, minus 1 over d mu of my ensemble F, and then F1 of Tz as 1/2 minus 1, 1 d mu ensemble F. I plug it in again, and I leave you as an exercise, but the exercise is solved in the notes so that you can go step by step through it, that if you do the same thing here, you will find as a result that the F0, the angular average of my ensemble average distribution, which, by the way, is basically equivalent to this n that I introduced, obeys the following equation. Where this coefficient k is, if I didn't do any mistake in the algebra, which is possible, of course, okay? It's an appropriate angular average of my inverse diffusion coefficient in terms of pitch angle. Now, forget about the details here. What is important is that we find again the same result, right? It goes as 1 over this, just like before we found that it goes 1 over this, and that's the same physical origin. Now, why I went through this is just because if you open a textbook, sometimes you find that approximation, sometimes you find that approximation. The physical content is the same, okay? And there are names associated to these things that I won't spend time on, but I mention in the notes so that you are not shocked if you find these names for these different approximations. There is another important point that I want to make concerning, well, I will make it concerning this second approximation. Basically, we have stopped in this decomposition to these leading terms. I could go on, right? Is this justified that I stop at the 0th and the first moment? Is there a hierarchy that makes sense and then justifies this approximation? The answer is yes. You can immediately see from this decomposition here, once you plug it in here and you follow the steps of the solved exercise in the notes, what you will end up with is an estimate, which I just write down here. The estimate is the following. The ratio of F1 term with respect to F0 term is given by minus k gradient F0 over F0, and reinstating for once the speed of light, here there would be a speed of light. Now, this one is what? Is the variation of the average distribution of cosmic ray over space. A typical configuration that I gave you yesterday is that basically the magnetized halo of our galaxy is few kiloparsec thick with respect to the 100 parsec of your disk. So basically I told you that this is the area populated by cosmic rays because it's magnetized, and the typical thickness is few kiloparsec. So another way to understand this is that the density of cosmic rays goes from the value that we measure at the Earth to 0 over few kiloparsec. So an estimate for this is of the order of F0 over few kiloparsec. This is purely empirical. So at the end of the day, this ratio has roughly the value of k over c times few kiloparsec. And I leave you as an exercise to show that this thing is always much smaller than 1, provided that the cosmic ray is diffuse. This is solved in the notes. So you just have to read them. Okay? So the only way for this to exceed unity would be to say that the cosmic ray propagate superluminally, faster than the speed of light. So in fact, this ratio is much smaller than 1, as long as what we did makes any sense. And by the way, this is also the estimate that you can get for the typical anisotropy in the cosmic ray flux. Because you remember that F0 is my average, and F1 is my dipolar term, just like in that expression. This is the isotropic piece, and this is a dipolar current term. Yes? Why do you have factor 3 there? No, this is just conventional. You could have omitted it, and the only difference would have been, I erased it. But in the equation I had, there was 1/3 gradient of n. This 1/3 would change. But this is just to agree with the standard definition of J that is used in the literature, which is the physical current, actually. If you wish, has to do with the three-dimensional nature of space. So, I hope I convinced you that you can do a little bit more formal restatement of what we argued about yesterday, based on the tools that was introduced this morning. Okay? In both cases of these two approximations that describe the heuristic derivation of yesterday, you end up with the same conclusion. The average, the ensemble average and angular average distribution of cosmic rays is described in terms of space evolution by a diffusion equation. And the diffusion coefficient in space is inversely proportional to the angular diffusion coefficient. Okay? On top of that, you can argue that it's meaningful to expand your distribution in terms of angular moments, if you wish, that the dominant term is the isotropic part, and there is a first leading correction, which is a dipolar one, this current piece, and the ratio of the two is given by this estimate. This is not surprising, because another way to describe this piece, as I told you, is that there is a relaxation process towards an isotropic distribution, which is what happens if you have any term that tends to change your direction fast enough, okay? That's what happens in a heat equation, right? Even if you start with a concentrated source of heat and you wait some time, what happens is that it becomes homogenized. So you go towards from an anisotropic configuration to a more isotropic one. Okay. What can I say? Okay, I won't say much about the ways to solve this equation or associated equation. Let me just say a few generalities. We will come back to a more simplified form of this equation at the end, the 5th lecture, to give you some, well, it's a more complicated in terms of physics, but more simplified in terms of mathematical structure that we can solve analytically. But let me mention the fact that although you see this tensor here, I wrote before the eigenvalues of this tensor is really a tensor. So the diffusion is expected to be anisotropic, okay, around. So there is a difference between diffusion along the magnetic field and across it. However, in phenomenological studies, for instance, computing the cosmic ray flux at the Earth coming from sources spread out all over the galaxy, what happens is that what you call the regular field is more local, right? So it changes if you move from that direction in the galaxy to that direction in the galaxy. So at the end of the day, what people implicitly do is to do a sort of meta-average. So you average over the direction of the regular field as well, which locally is well defined, but on large scales it changes again. So you replace these quite strongly anisotropic tensor with an effective isotropic piece that you get out of your derivative term. And that's what is typically constrained by looking at the data. For instance, the boron over carbon ratio mentioned yesterday, the secondary over primary ratio. So in order to do the inversion problem and go back to the microscopic diffusion tensor, you should also add some information on how the regular field changes all over the galaxy, okay? So, which is typically not done in phenomenological analysis. So this is just a caveat why you would see many phenomenological papers, including ones using numerical tools like GalProp, you might have heard about that, or Dragon, using an isotropic approximation for the diffusion tensor. It's not that people forget that this is isotropic, it's just that basically you are doing another sort of average over these domains if you think of regular field. So one thing I wanted to mention about how you solve, at least conceptually, this type of equation in slightly more general mathematical terms. Probably you have heard about this before, but basically, if you have an equation of this type, derivative with respect to t of n minus k of n equals some source term, because in general you have to add the sources of cosmic rays. A rather general technique that is used is the green function technique. So basically, if you can solve the associated problem on knowing this function g, which in general depends on the energy or the momentum, such that it solves this equation, then with appropriate boundary condition, which is a non-trivial thing to impose, then the solution to your problem will be given by a convolution of this function with this source term. This is in general three-dimensional, but let me simplify a little bit the notation. In general, P. Okay? This is the idea. How do you solve this? In general, the tricky part is to find the right function that obeys the boundary conditions of your problem. Let me just illustrate one case, which is the simplest one, where you have basically vanishing function at infinity. This is free escape at infinity. Okay, we won't use this for any practical application, but be aware of this more general way, more mathematical way to solve it. Basically, what happens is that you solve it by Fourier transform, okay? You write this as some term that depends on a wave number times the e to the minus I omega t plus k z, etc., etc. You plug this decomposition inside this equation, the same trick Pasquale was mentioning this morning. The derivative with respect to time brings down a factor of omega. The derivative with respect to space brings down a factor of ik. So this becomes, in Fourier space, it becomes an algebraic equation. You use the expression of delta as the same decomposition I used yesterday, remember? This is 2 pi delta y. You do the same trick, and then you end up with this expression for g. The integral d cube k d omega 2 pi to the 4th power, and then you have an exponential function I k dot x minus x prime divided by that piece that comes from there, which is in general dependent on energy or momentum. And if you know what I'm talking about, you can take the residue of this integral. You can express this in a more intuitive way. If you don't know what I'm talking about, just trust my result. For k t minus t prime. If t is larger than t prime, otherwise it's 0. Okay? So if you have solved the heat equation before, you have found exactly the same thing. And by the way, if you have found the propagator of Schrödinger equation, the free one, you would have found exactly the same thing. Okay? It's always the same. Apart from the factors of I, etc., etc., this is the free particle Schrödinger equation. It has exactly the same mathematical structure. Do you recognize it? So exactly like a wave packet in quantum mechanics, if you wait time, what happens is that its variance, you see this is a Gaussian thing, its variance grows linearly with time. And if you want to have some fun, just like you do in quantum mechanics, now it's more familiar, the quantum mechanical version than the classical version, but you can compute average values of some observables, right? So in particular, you can compute the average value of the distance from the origin, r squared. This is nothing but the average value of the sum over I of xi minus xi prime square summed over n, where n is the dimension of the space. This little n is the dimension of space that I want to keep free for now. If you take this, which means making the integral of this expression times this expression divided by the norm square, just like you do in quantum mechanics, what you would find, this is a Gaussian integral, you would find 2n kt. Now this is just a parenthesis which serves the purpose to justify what I told you yesterday. What is the typical displacement a drunk guy variance of the displacement some drunk person would travel bouncing in a random motion? It's linear in time, the variance. And the coefficient of proportionality, we argued, is going to be proportional to the diffusion coefficient of your problem. I told you, forget about the numerical factor. This depends on the dimension of space-time. This is 2n. So it's 6 for three-dimensional space. Okay? And from this, I also suggest to compute at which energy, for a given energy dependence of this diffusion coefficient k here, I give you the result of a fit to actual data, and I ask you to check up to which energy you expect that the diffusion coefficient is a good the diffusion approximation is a good approximation for the propagation of cosmic rays. Again, this is based on the fact that you can argue that for a source at distance d, the quantity 6k over d can be taught as the effective velocity, just from this result. Okay, How much time do I have? We don't know. The organizer has left, so we are half an hour, 20 minutes. Okay. So, what can I say now is that what I told you is just like an epsilon of the whole story, because as Pasquale was mentioning this morning, these waves, these fluctuations in the field are not actually static. These are waves. Okay? They come out of this dispersion relation. And you saw that there was, okay, at least he said that there was some relation of the type omega VA times K, and this VA is equal to B0 over 4 pi density. So all what I said yesterday made the assumption that these fluctuations were static. If you remember the sinusoidal fluctuation that I added, it depended on space. There was a kz, but it didn't depend on time. Okay? So it's like the cosmic ray is looking at a frozen background which is fluctuating, not something dynamically moving. But from the argument, at least qualitatively what Pasquale said, you know now that actually these kind of fluctuations are dynamical. Okay? They propagate with a given velocity. So we should modify what we said yesterday. There will be modification and additional terms due to the fact that these fluctuations are moving. More formally, the frame in which the fluctuations are at rest, for which what I told you yesterday is correct, does not coincide with our laboratory frame. So we will have to do some gym associated to this change of frame. So in the notes, I will give you all the steps. Today, for clarity and for lack of time, I will just give you the logical step of what you have to do if you want to go from the problem we solved yesterday and today to the more general solution. By the way, there is another reason which should convince yourself that this cannot be the whole story. If you look at this equation, or even the equation with the sources, there is clearly something that is disturbing, namely that there is no term where the energy is varied. There is no derivative with respect to energy. So if this is the whole story, how do you change the energy of these particles? How do you have acceleration in the first place? So there must be some other effect which we have neglected. And as Pasquale said, basically you cannot have, in generic condition, some large coherent electric fields. So this fact that you have moving perturbation in your lab frame is actually very important, because these are now magnetic perturbation, but in a frame which is moving with some velocity with respect to you. So you do expect that there is some associated electric field, some electric field E, which is basically B dot V, where this V is this velocity of your magnetic perturbation. Okay? In general, this velocity V we will write as the sum of some macroscopic average velocity U plus some delta V sort of fluctuation. So you may think of these as, for instance, a coherent motion of your plasma, and these as the random motion of these things within this plasma. Okay? So far, so good. Let me erase this part which is not relevant anymore. Okay, now we repeat the same decomposition we did before. Okay, or an equivalent one. So I rewrite f. Okay, this f is what I was calling bracket f before, but in order not to repeat the bracket every time, now I will just call it f for simplicity. 1 over 4 pi n plus, okay, 3 over 4 pi. Okay, I will introduce this vector w instead of the current so that I am a little bit more lightweight on the notation. So n is exactly the omega p of this f, and this vector is nothing but the integral over the omega p dot of f, and there is a difference of a factor of velocity between the two. So basically J, the current I introduced before, is V times W, which is also P over E W. The other difference I'm doing here is that now I'm not considering any more ultra-relativistic cosmic rays. I want to retain the velocity different from C, different from 1. Apart from this technical detail, I do the same thing. I plug this into that, accounting for the fact that I have this definition of velocity there. And what I get is this coupled system of equation. Yes. This is just another way to write the integral over the angular part of this piece here, which I'm writing short notation, the f over the t collisional, because it behaves like the right-hand side of a Boltzmann equation. But if you don't like this notation, just keep this one, okay? And the other equation which is coupled to this one will be this one. Why there is some new term? There is some new term because now you have an electric force there associated with the fact that your scattering centers are moving. But this is not the whole story. And then the whole game is to write this thing in this frame. Because I told you how to write this thing, which is equivalent to this piece here, in the frame where the scattering centers are at rest. This is nothing but this term minus nu theta theta f minus n over 4 pi. This is exactly the same thing. The difference is that this writing is valid in the frame where these scattering centers are at rest. Okay? So basically, I know how to write this term there. This is nothing but minus theta theta f minus n over 4 pi. Or if you wish, this is minus 3/4 nu theta theta w pi over p, and this is a summed the convention of summing over the repeated indices. So I know how to write this one. This is equivalent to what I wrote before, but I have to change frame, okay? So how do I deal with this change of frame? Well, I use an important fact, which is that the density in phase space is a Lorentz invariant. Why? I told you that, is it still written? Yes. This thing is a number of particles, is a differential number of particles. So at least in a Minkowski case, how many particles there are in my system won't change if I change frame. So I use this fact, and I know that in the two frames, the one at rest with respect to the perturbation and the one of the lab, the distribution function writes the same way. So if I use a bar for the plasma frame, I will have that f of p. I'm omitting the x variable because it's not really relevant here, is equivalent to f bar of p bar. What I write in the wave frame or the lab frame should be the same. And then I have the transformation between the two, assuming that my change of frame is non-relativistic. Basically, I'm assuming that this thing is very small compared to C, which you can check explicitly. For typical values of magnetic field in the galaxy and the density of the galaxy, the matter in the galaxy, you can compute this V, and it turns out to be of the order of tens of kilometers per second, which is much, much smaller than the velocity of light. So this is a non-relativistic transformation, in fact. And then it's linked the momentum in one frame with respect to the momentum in another frame by a Galilean transformation, if you wish. Okay? So I won't give you the whole tedious derivation, but basically you use this, you plug into this, and you derive the transformation law for F, for W, and etc. If you do that, you can rewrite this term, which I know how to write in the rest frame, into the frame of the lab, and I can replace into this right-hand side. Okay? In the notes, these things are done step by step so that you can check them. Hopefully, I didn't do any mistake. If you do that, and you bear with me, you will end up rewriting our Vlasov equation or better, this coupled system of equation for N and for W with the right-hand side. I write it here in components, d over dt of N plus P over E dWi over dxi, some convention, plus E over P square, derivative with respect to P square Wi epsilon I j k omega j u k equal, okay, this is, just 1 second, okay, sigma n, okay, so this should be nu tau tau p cube E respect to P I don't have enough space, so I will write it on the second line. No, maybe there is enough space. P cube times a parenthesis. And this parenthesis is Wi Ui plus E third U square dn over dp plus E thirds delta V square dn over dp. And there is an analogous equation for the W that I won't write it explicitly. You see how just by changing this frame, this becomes a mess. Huh? Anyway, if you do the usual trick that we did before, namely that in the second equation, this equation for W, you will neglect the W with respect to the high frequency part. Remember, before we said that dt of j was much, much smaller than actually nu tau tau j. And we do the same thing here, again. If you do that approximation, what you find is that Wi will be equal to minus E over P Kej dn over dxj minus E third Ui dn over dp. And this Kj now, Ij, is 1 over 3 nu theta theta, the stuff that we wrote before, times a factor p over e square times the same ratio that we wrote before. So it has acquired a factor p over e square because I didn't neglect the fact that v is different from 1, from c. Once you have this expression, which is nothing but the replacement of what we had before, remember that we had that ji was minus kij gradient of jn. This is exactly the same, what replaces the previous relation. And now we plug into the first one, and we have a closed equation for n, which is what we care about most. So let me write it down, and then we discuss a little bit the physical interpretation of what we got. All these derivations are not important technically. What is important is that you understand where they come from. Minus derivative with respect to xi, ij. It doesn't mean you shouldn't do it once in your lifetime. The first time you do, you learn something. The second time you do, you just bore yourself to death. So.
And the third?
The third you just do if you are hired as a professor and you have to do it to write some notes. Or if you have some sort of pathology. This is again summed over I, P dn over dp equal 1 over p squared derivative with respect to p of p squared kpp dn over dp, and this kpp is nu theta theta e square delta v square over 3. Okay, so what have we learned? There are new terms appearing with respect to the previous equation, okay? The previous equation was basically this one. Huh? Now we have additional terms, and you see that these additional terms go to 0 if I put U and delta V to 0, as it should, because the only thing I did was to go to a different frame. Huh? So if I put U and delta V to 0, this is 0, this is 0, this is 0, because there is a delta V here. So far, so good. We cannot be too wrong. Huh? What do they mean physically? Okay, this first term here is advection. Okay, so clearly, if you have a plasma that is moving coherently, your distribution of cosmic ray evolves because there is a sort of wind. Huh? So it's not so strange. It's an advective derivative, if you have heard about that. You know? If you add this to the time derivative. Okay? It's the same sort of term that appears if you go from a Euler description to a Lagrangian description. Huh? You move with the plasma or not. And it's present, logically, for at very least some physical reason. I told you that most of the stars and potential sources of cosmic rays are in this plane, and far away from the galaxy, the space is basically empty, so it's not unphysical, and it is seen that there is a sort of wind blowing from the plane of the galaxy towards the outer edges of the galaxy, okay? Just because of that, you should expect that there is some movement, there is a gradient. This term is quite important, and this has to do with adiabatic losses or gains. If you have a gas that is compressed or expands, there is an associated change of the energy, internal energy of this, okay? And this is translating into a term which changes the energy of your distribution of particles, okay? This is extremely important for what Pasquale will say about acceleration at shocks. This is basically the physical origin why particle can get accelerated at a shock. Another term that you see is this one, okay? And this notice depends on the fluctuations on the delta V with respect to this coherent motion. And this is known as reacceleration, or from a more mathematical point of view, look at this term. It looks like a diffusion term, but in momentum space or in energy space, if you rewrite it. So what it means is that since you now have random waves, there will be a random electric field. And this electric field is capable of accelerating this particle diffusively. So your particle of a given energy will now move in a random way in energy space as well. Okay? It will typically broaden the distribution of the energy distribution of your cosmic rays in energy space. Okay? And it's proportional to the square of this, which order of magnitude, this term is of the order of the Alfvén velocity, of course. Another way you find this relation written typically is that KPP times KXX, or the space diffusion coefficient, is P square delta V square over 9. Now, this is also what is associated to the so-called second order Fermi acceleration mechanism. I don't know if Pasquale will mention it. So in general, in the galaxy, in the propagation, it's rarely dominant, unless you are at relatively low energies. So it's useful to describe the fine aspects of the spectrum around the few GeV, but it's not the source of the cosmic ray acceleration. However, it can play a role as a mechanism to accelerate particles in a number of astrophysical objects, okay? So it's good that you know what we are talking about, okay? Now, this equation that I wrote down, this one, plus an eventual source term that you have to put once you know where these particles are accelerated, which is the other lecture goal, basically describes most of what we care about collisionless. These equations need to be supplemented by additional terms that have to do with energy losses. Energy losses are a completely different beast because now they fall in the other category of interactions which we haven't treated yet. I will do in third and fourth lecture, namely the interaction between particles and the interactions between particles and fields, background fields. So before we go to the solution of this equation in some benchmark cases, I want to introduce these energy losses. So third and fourth lecture will be devoted to describe these energy losses. Then we will see how these terms modify. So there are additional terms in this equation accounting for these energy losses. And then I will show you some solution of this equation, or a bigger version of it, associated, for example, to this boron over carbon problem, the determination of diffusion coefficient, and possibly some indirect dark matter searches. Just 2 comments. There are some approximations done here. The most important approximation is that I used is that this thing is non-relativistic. I used the transformation, the Lorentz invariance of my distribution function, and I did a Galilean transformation. So I'm assuming that these scattering centers are moving non-relativistically. This is okay for basically all galactic phenomena and for cosmic rays. It might not be a good approximation if you want to study propagation in environments which are very different from our interstellar medium. A more conceptual level, I did a different type of approximation, which is what Pasquale warned you not to do. Namely, I assume that the 2 things are decoupled, right? I assume that there is a background of these fluctuations, and I want to describe the movement and the evolution of cosmic rays on this background, but I didn't couple the 2, okay? If you do that, many wild things can happen, which are very, very important for modern theories of acceleration in particular, but as we have argued in the recent past, they are also important possibly for the propagation of cosmic rays, okay? So be aware that this approximation is not the whole story. And if you ever use a numerical tool like Galprop or Dragon, etc., that's the kind of approximation that is basically plugged in. So some of these nonlinear phenomena are not described, nor possibly can be described within the same framework. And I would stop here because I think I'm already over time. Thank you for your attention.
I know you know the rules of the game, so.
By now you are...
Which I didn't set myself. So. You don't want to disappoint him. Have you seen his arm?
It was a very dense one, but I had to do it. I can promise the next ones will be easier. More boring, but easier. But is it clear what I did conceptually? Not the steps. Forget about the steps. Okay? I just used what I hope I convinced you about yesterday to argue about a special form of this right-hand side in the Vlasov equation that this morning was derived. I argued that these can be described, this effect of fluctuation can be described just as a relaxation towards an isotropic situation, or equivalently like a diffusion in pitch angle. If I do that, I get the heat equation. The average ensemble distribution of cosmic rays relaxes, propagates in space like heat wave, a heat in a metal bar. On the top of that, I said if we relax the approximation, these scattering centers are fixed, which is what I did yesterday. We will gain new terms. Okay? These new terms are derived in a conceptually clean way, right? We know how to write our collisional term, this right-hand side, this relaxation term, in the frame of these waves. You move to the frame of your lab system, and you see what new terms appear. And these new terms have an interesting physical meaning. Okay? Advection, if the plasma is moving, particle get a term, a special term associated with it. Some energy changing term, which is very important, associated to the compression or rarefaction of the medium, you see here. This is a div U. So if there is a compression or a rarefaction, there is an associated change in the energy of your particle. Okay? And then there is another term which is associated to the gain, sort of stochastic gain of energy, due to the fact that these scattering centers have also a random motion. Okay, these are the new terms entering there. Please.
So I have a question about the dispersion relation in comparison to what we saw this morning, because this is a lot more complicated, and I'm guessing there isn't a clean regime where you have the dispersion relation for acceleration go to dispersion, right?
Here, I don't know why you claim it's a lot more complicated in a certain sense. I mean,
which one? Just functionally compared to the dispersion relation.
The dispersion relation tells you the link between the frequency, if you wish, and the wave number. Okay, and it tells you in the specific case mentioned, or in the more general case, was something like omega k equals 0, right? This is the dispersion relation. Right. So what the dispersion relation is telling you is what are the modes that are possible in a given system. Okay? Now, here, I didn't use really the dispersion relation. This has to do with the properties, if you wish, of these centers that are moving, which are characterized by this velocity. The only place where I use this is in estimating here this delta V. But in general, this kind of thing, it does not depend on the dispersion relation that...
But what is the dispersion relation that you're referring to? It's much more complicated.
Can we just not Fourier transform this equation?
Okay, no, that's where the problem is probably. Yeah. So this morning when I found this, I discussed the dispersion relation. What I was trying to do is to apply the Blasius equation to the gas. What Pasquale is doing, the other Pasquale, is to apply the Blasius equation to the cosmic rays. So it's the one that I didn't almost at all discuss this morning. So this is what you get for the cosmic rays. And then you have another two for the electrons and ions, which is not including here, which is what he just said right now. I'm assuming that these perturbations are there. I don't care, how they're produced. So they're produced because of the interaction between the three velocity equations, electrons, ions, and the cosmic rays. So when you want to linearize your problem, you try to ignore this complexity. And so you say, okay, there is a plasma on one side, and the plasma gives rise to that omega k VA. And then there are the cosmic rays on the other side, and they do this. And then at some point we will have to put them together. This will happen somewhere down the road.
So I'm assuming, again, that I'm decoupling the two problems, right? I'm assuming that the modes that my system supports are determined by these background ions and electrons, and I'm now assuming that my cosmic rays propagate in this environment, and they do not affect the modes. Okay? I said in the final minute or so that I'm assuming that there is no alteration, if you wish, into that coming from this, which numerically speaking if this was a linear theory, well-behaved, blah, 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 it's not so crazy, right? What Pasquale said, you have something which is 10 to the minus 9 of the background plasma. It's not so crazy to say, okay, I treat this like a test particle propagating in this environment. Of course, you forget that there are instabilities, okay? And plasma physics is a zoo of instabilities that can arise. There are nonetheless some regimes, as Pasquale explained, where this turns out to be not a crucial approximation in spoiling completely what we are doing, but keep in the back of your mind that we are factorizing the problem. We take the background plasma to determine the properties of the medium and the modes of the medium, and so things like that, and I'm now propagating the cosmic rays in this. It's not because I'm evil that I do that, because this is what 99% of the literature does.
Yeah.
Huh?
So maybe if I can rephrase once more the same concept. So in the terminology that I used this morning, you can write a velocity equation for each component, right? And then I warned you, I said, be careful because the coupling between the two is in that delta E and delta B.
Yeah.
Okay, so where is this delta E and delta B here? So the delta B, let's forget for delta E for 1 second.
Yeah.
The delta B is the term that leads to
Yeah.
this. So basically, what Pasquale is assuming is that the delta B, the magnetic field, is only produced by the plasma, or something connected to the stuff that that is not including, and it talks with the cosmic rays only through the scattering term. So the delta B has one effect only. It changes the direction of motion of the particles.
Yes.
What about the delta E? The delta E is the term that leads to this.
Yeah. Yes.
So the physics of it is that one particle sees this tiny delta E, and it can change its energy by a little bit. How much? Well, about VA over C. But in which direction? Right. If the wave is, you have this electric field, right? And the particle is going through. Depending on how it's interacting with this electric field, this can be a plus or it can be a minus.
It's a random.
So on average, the particle momentum can either increase or decrease. But then, of course, on average, it can only increase because it cannot go through zero, right? So phase space is nice in the sense that there is an origin and then there is infinite space around. So if you had to guess, you would randomly go towards the momentum P larger and larger. But how quickly? Well, the problem is that on average, you can lose or gain. Therefore, the velocity of this process is roughly C over VA times squared, times longer than 1 over this.
Yes.
In other words, in the same time that it takes for the particle to change the angle by 90 degrees, which is 1 over this, the particle has changed by VA over C squared times,
and you see
which
here,
is ridiculously small.
This diffusion coefficient is proportional to this because, well, that's what drives the whole thing. And then there is a delta V square, which in natural units, this is delta V. This is like VA square over C square, which is a small number, right? So it's a relatively slow diffusion in momentum space compared to this natural scale of diffusion in angular scale, in angular space, okay? So that's the origin of your...
So the fact that you have only very few cosmic rays is being used here to say the electric and magnetic fields are only produced by the plasma, the cosmic rays don't, but they feel the action of it through these two terms. We will see somewhere down the road that when you relax this approximation, terrible things happen. So...
I think it's a good note to leave with the idea of these terrible things happening. Maybe we can take all the other questions in the afternoon. Please bring them. Thank Pasquale again. All right, so the afternoon, you know, it's back at 3. Your USB keys are here. The owner of this one, I couldn't load it, so please send it to me via email. And those who still need to give it to me, they will do so tomorrow morning because I won't be here this afternoon. Okay? I will see you tomorrow morning at 9:45. They're going to be here at 3 p.m. One thing, the videos of all the lectures are online. So if you go to the webpage of the school, it's videos and files. The videos of the first day are already online. Some lectures are online. COTAS exercises are online. Okay? The videos are extremely useful. You can use them even on your phone while you're doing exercise or whatever. So it's nice.